So in part C, we are told that after a long time, the switch has been in position A, we switch it to position B. And we're asked immediately after we switch it to position B in which way the current will flow. So what we need to note here is that the initial charge on the capacitor will be positive on this side and negative on this side because it has been connected to this battery which was in this arrangement. So we know that conventional current flows from the positive side, so it will flow to the right. And the reason for this is because the top plate of the capacitor is positive. The top plate is positive and therefore it has to flow to the right. And then in part 2, we're asked to determine the expression for the total charge on the capacitor 2 after a long time, if initially we had a charge of Q0. So what we note is that the potential is the same across them, and we see that the second capacitor is 2 times larger than the first capacitance, as we see C and 2C. And so since they have the same potential across them as they're connected across one wire, they must be splitting the charge in a 2-to-1 ratio. So the second capacitor must be charging twice as much as the first capacitor. Therefore, this will be 2 over 3 Q0. So that C1 can be 1 over 3 Q0. So we see that this is twice as large, and they add up to 1, conserving charge. So conservation of charge is very important here. Their sum has to be the same as the initial quantity. And then in part 3, we're asked to derive an expression for the total energy dissipated by the two resistors immediately after time t1 until new steady conditions are reached. So what we need to note here is the types of energy we have. So we need to see that initially only our first capacitor has energy, and afterwards both capacitors will have energy, and the difference of these two states will give us the dissipated energy. So the change in energy will be given by the final energy minus the initial energy. So the final energy will be the energy stored in two capacitors individually. So that can be written as 1/2 times Q squared over C. So 1/2, and then we have the capacitance of one of them, let's say the first 1 over C. The charge, as we have discussed, will be Q0 over 3 squared, and the other capacitor will have the same 1/2. It has a capacitance of 1 over 2C, and it has a charge of 2 Q0 over 3 squared. So this is the final, and from this we need to subtract the initial amount of energy stored, which is simply 1/2 Q0 squared over C, as in this case only our first capacitor is storing any energy. So once we have this, we can simplify this. So this will be Q0 squared over 6C minus Q0 squared over 2C. And if we subtract this, then this will be minus Q0 squared over 3C.